Okay, so in this penultimate part of the lecture, I want to look at a practical example of linear regression conducted using the statistical software R, and we'll also be following this example a bit further when we meet in class. So the example that I've chosen to use here is one where we're going to use regression to calculate the age of the universe using data from the Hubble Space Telescope. So our question is, how old is the universe? And the standard Big Bang model states that the universe expands uniformly and locally according to a law known as the Hubble-Lemaitre law. And it's given by this equation here, where y is the relative velocity of any two galaxies separated by distance x, and beta is known as the Hubble constant. Now, I'm a statistician, I'm not a physicist, so I don't know, this is not my area of expertise, but the way I'm interpreting this is velocity is equal to distance or displacement over time. So beta, or the inverse of beta, should give us time. That is, it should give us the age of the universe. And that is indeed what the physicists tell us. The approximate age of the universe is given by beta to the power of -1. But we don't know the value of beta, or assume we don't know it, and we want to estimate it from observations on y and observations on x. And that's actually what the Hubble Space Telescope is able to give us. We've got data actually available in R on 24 galaxies at different distances from the Earth. And the data records three things: an ID, that's just a label identifying the galaxy; the variable y, the galaxy's relative velocity in kilometers per second; and the variable x, the galaxy's distance in megaparsecs, 1 megaparsec being equal to these, having this equivalence in kilometers. And that's a scatter plot of the Hubble data. And as you can see, it looks to me as if a straight linear model is going to fit the data pretty well. So we're going to estimate the following model: yi equals alpha plus beta xi plus an error term, and we're going to do it using least squares in the way that we have described in the lecture. And here's the R code that we're going to do to estimate the model, and feel free to use this at home or when you're going through that after this lecture, just to see how it works. First thing we're going to do is we're going to load a library known as GAMR. The only reason we're loading that library is it contains the Hubble data, and then we're going to extract the Hubble data from this library. This here just plots the Hubble data. This reproduces this scatter plot here, I believe. Velocity on the y-axis, distance on the x-axis. And then we're going to perform a least squares estimation. And the least squares syntax in R is, we're going to call it, our Hubble model is a linear model where we're regressing y against x using data Hubble. This command here summarizes the regression results. This creates residual plots. We'll look at this in class. And finally, the final part of the model, I calculate the age of the universe. As you know, the units of the data are, megaparsecs and kilometers. So I've used a conversion here to convert the age of the universe to years, and also to calculate confidence intervals, again converted to years. So you can have a look at this in your own time. So this is what happens when we conduct our least squares regression. This is the output that we get from R. It's shown below. And what I want to do is, the next slide provides comments on this output. And I just want to go through provides comments on this output. And I just want to go through and explain what the R output is telling us. Okay, so first we have this thing here called call. And all this has done is simply returned the formula in R we used to estimate the model. So this is telling us we used the formula in which y was regressed on x with using data Hubble. The next part of the output gives us some statistics on residuals. It's reporting the quartiles of the residuals. So the minimum value, the first quartile, the median value, the third quartile, and the maximum value. And we talked about quantiles and quartiles last week. And the idea of reporting this really is we've assumed that our error term is normally distributed with a mean of 0 and constant variance. So we expect symmetry around 0 around the mean or around the median, and that is approximately shown by the model residual. So the minimum value is -735, the maximum is 558, and the median is -22. So it's not that far away from 0, and the third quartile and the first quartile not too far, fairly symmetric, but not entirely, but fairly symmetric. So that's just to give a quick indication of how our residuals are looking in terms of the assumptions that we're making about them. Next is the actual estimates. This is the coefficients, the parameter estimates that we've got from these squares, and there's different columns here. The first column gives us the estimate themselves. So the least squares estimate of alpha, the intercept, is 6.696, and the least squares estimate of beta is 76.127. The next column gives us the standard error of those estimates, calculated in the way we described earlier. So the standard estimate of alpha is large. Remember, the t-value is the ratio of the estimate to its standard error, so the t-value is low with a high p-value. So what this tells us is, in this model, the intercept is not statistically significant. It doesn't have a level of statistical state. This is well below the critical value of t, and the probability of obtaining this is high. So actually, this means that we cannot reject the null hypothesis in this model that alpha is in fact equal to 0. We cannot reject that null, and we can in a sense almost ignore this estimate. It's not particularly meaningful because it has no statistical significance as shown by the t-value and the p-value. The standard error of beta is relatively small relative to the estimate, so when we calculate our t-value, t is bigger than the critical value. So we can reject the null hypothesis. Actually, we can reject it at significance level below 0.001. So it's statistically significant. So we have a parameter, beta hat, that's going to tell us about the age of the universe that, according to our model, has statistical significance. Okay, next in the regression output, we have the residual standard error, 264 on 22 degrees of freedom. Remember, residual standard error only has meaning in relation to the actual units of y, and in this case it indicates that the regression model predicts galaxies' relative velocity with an average error of 264.7 in units of y. R squared and adjusted R squared indicates that almost 75% of the variation in y has been explained by the model, so the explanatory power is pretty good, about 3/4 of the variation in y explained by variation in x. And the S statistic is large and significant, indicating that the explanatory power of the model has not arisen by chance. And that's the comments on the model output there. So, how old is the universe then? Using the estimate beta equals 76.127 from our model and converting to years using the code here, this is what converts to years, and you can, it just makes a conversion from units. Our model estimates the age of the universe at just under 13 billion years. At the 5% level, the critical value of t for degrees of freedom 23 is 2.069, and the corresponding 95% confidence interval can therefore be calculated by the estimate minus the standard error times the critical value of t. This gives us these values here. It allows us to reject hypothetical values of beta above 95.87 and below 56.384, but any hypothesis within these limits is not rejected given the regression results. And that gives us a confidence interval for the age of the universe as being between just over 10 million years to just under 17 million years. And that's quite a big interval, 7 billion years. And we're actually going to do better than that in class with an improved model. But that's the result we've got, around about 13 billion years for the age of the universe. And you can go away and Google and compare that to what scientists think the age of the universe is from other sources.